2019, question 3. A student is given 50.0 milliliters of a solution of sodium carbonate of unknown concentration. To determine the concentration of the solution, the student mixes the solution with excess 1.0 molar calcium nitrate, aqueous, causing a precipitate to form. The balanced equation for the reaction is shown below. Here we go. Part A, write the net ionic equation for the reaction that occurs when the solutions of sodium carbonate and calcium nitrate are mixed. So we are given the complete balanced equation for the precipitation reaction here, and we are asked to write the net ionic equation. So what's the difference? The complete balanced equation shows that ionic exchange occurs. So that means the anions present, the CO3 2- and the NO3 1- switch places. The carbonate polyatomic ion switches from sodium to calcium, and the nitrate ion switches from calcium to sodium. However, this doesn't actually represent what is occurring in the solution. So everything that has AQ in parentheses after it, so the sodium carbonate, the calcium nitrate, and the sodium nitrate, these are all dissolved in solution. So that means it's dissolved into the individual cations and anions. So the full ionic equation would look like this. So everything with an AQ can be separated into the cations and anions that make it up. So we have 2 sodium ions, aqueous, plus a carbonate anion, and a calcium 2+ cation, and 2 nitrate anions, and this goes to 2 sodium ions, aqueous, and 2 nitrate anions, and our solid, calcium carbonate. So we've separated everything out into individual dissolved ions that are in the aqueous state. But we don't separate out the calcium carbonate into ions because it is solid, not aqueous. So looking closely at this full ionic equation, we see that sodium ions and nitrate ions appear on both sides of the reaction. And these are called spectator ions. They maintain the neutrality of the solution so that charge doesn't build up, but they don't participate directly in the precipitation reaction. So we will discard these, and the end result is the net ionic equation. So let's discard sodium because it appears on both sides of the arrow, and nitrate, and it's called the net ionic equation because we remove the spectator ions from the complete ionic equation and only include the ions or molecules that are directly a part of the reaction. So our net ionic equation is what's left. So we have carbonate anion plus calcium 2+ cation goes to calcium carbonate solid, which is our precipitate. And that's the net ionic equation. The balanced equation for the reaction that they give us in the problem doesn't fully represent what's going on because the substances with aqueous are dissolved into their cations and anions. The full ionic equation includes all spectator ions, but the net ionic equation removes the spectator ions and only includes that which is directly part of the precipitation reaction. Part B. The diagram below is incomplete. Draw in the species needed to accurately represent the major ionic species remaining in the solution after the reaction has been completed. So in the diagram we see sodium and nitrate ions and the solid calcium carbonate precipitate. And they tell us that we're missing an ion. So if we look at the diagram, we see that we have sodium cation and nitrate anion present, and also solid calcium carbonate. That's the precipitate that has formed at the bottom of the container. So all of those are shown, but we're missing a major ionic species after the reaction has been completed. So the calcium ions and the carbonate ions precipitate out as calcium carbonate. The only possible species that we would need to add to this solution would be a calcium cation or a carbonate anion. So let's look at what they told us. The solution is originally sodium carbonate, right? That's what they say. We have 50 milliliters of a solution of sodium carbonate. And then we add excess calcium nitrate. That means that all of the carbonate originally present in the solution, it's present as aqueous sodium carbonate, has reacted to form solid calcium carbonate. However, because we added excess calcium nitrate, we have excess calcium ions and nitrate ions. Nitrate is already shown in the diagram, so the missing major ionic species then would be the calcium 2+. All the carbonate should be in calcium carbonate precipitate, so we'll add a Ca2+ ion to the solution. The student filters and dries the precipitate of calcium carbonate, molar mass 100.1 grams per mole, and records the data in the table below. Part C, determine the number of moles of sodium carbonate in the original 50 milliliters of solution. So this is simply a stoichiometric conversion, and we're going to be looking at the original 50 milliliter solution of sodium carbonate. So from what we talked about in Part B, we know that all of the carbonate reacts to form solid calcium carbonate. So there will be excess calcium 2+ ions because we added excess calcium nitrate. So let's look again at the balanced chemical equation for the reaction. We know that for every 1 mole of calcium carbonate produced, we required 1 mole of sodium carbonate. Why is that? Because they both have a 1 in front of them in this reaction. So the calcium carbonate produced consumed all of the sodium carbonate originally in the solution, so we have a 1-to-1 molar relationship between the two, this sodium carbonate and calcium carbonate. So the mass of calcium carbonate precipitate collected, we first convert to moles and then use the 1-to-1 molar relationship to convert that to moles of sodium carbonate. So the precipitate was 0.93 grams calcium carbonate solid. They give us the molar mass of calcium carbonate, so we simply convert that to moles calcium carbonate by using 100.1 grams per mole. And then that will give us 0.0093 moles calcium carbonate. And we convert that to moles sodium carbonate using the 1-to-1 molar relationship of sodium carbonate to calcium carbonate. Right, because for every mole of calcium carbonate, 1 mole of sodium carbonate, because we know that the carbonate is the limiting reactant in this reaction. What we find is that we produce 0.0093 moles of sodium carbonate. And I mentioned that carbonate was the limiting factor for this reaction, and we know that because calcium is in excess. Carbonate is what limits the amount of calcium and carbonate that can be produced. They tell us we've added excess calcium, so what's limiting the production of calcium carbonate is the carbonate. Part D. The student realizes that the precipitate was not completely dried and claims that as a result, the calculated sodium carbonate molarity is too low. Do you agree with the student's claim? Justify your answer. So let's work through this logically. So they say not completely dried. So that means there was water in the precipitate that should not have been there. So the mass of the precipitate is artificially high and there is actually less than 0.93 grams of calcium carbonate. So the mass of the precipitate is actually something less. For example, let's say that instead of 0.93, it's actually 0.8 grams of calcium carbonate. So if we had used a smaller value, like 0.8 grams in part C, then the number of moles of sodium carbonate would decrease. So the actual molarity would be lower than the calculated molarity. So this is what we calculated for the number of moles of sodium carbonate, and the actual number of moles is lower if we were using something less, like 0.8 grams of calcium carbonate. So the actual molarity would be lower than the calculated molarity. Calculated number of moles is too high. The calculated concentration, or molarity, is too high. So the student is wrong. The calculated molarity is too high, not too low, because the calculation used an artificially high mass of calcium carbonate instead of the actual mass of calcium carbonate. Part E. After the precipitate forms and is filtered, the liquid that passed through the filter is tested to see if it can conduct electricity. What would be observed? Justify your answer. The question is, will the solution conduct electricity? And the answer is yes. And the reasoning is that because there are ions in the solution, namely sodium and calcium cations and nitrate anions, because there are ions in solution, the solution is able to conduct electricity. It's as simple as that. Electricity is the flow of electrons, negative particles, so we need ions, charged particles, to be able to conduct electricity. And this solution definitely has ions. The student decides to determine the molarity of the same Na2CO3 solution using a second method. When sodium carbonate is dissolved in water, carbonate hydrolyzes to form bicarbonate, as shown by the following equation. So we have a balanced equation and a weak base equilibrium constant. So part F, the student decides to first determine the concentration of hydroxide in the solution, then use that result to calculate the initial concentration of carbonate ion. Part I, identify a laboratory method, not titration, that the student could use to collect data to determine the concentration of hydroxide ion in solution. So what we want to find out is the concentration of hydroxide ion. So besides titration, what we could do is measure the pH with a pH meter. It sounds too obvious to be true, but it's as simple as that being another method besides titration that we can use. What we can't say is just that pH could be tested, or just measure the pH. We need a laboratory method, so using a pH method, or using a pH probe or meter. And this is valid, as we'll see in part II, that we can derive the concentration of OH- from pH, because it's directly related to the concentration of the hydronium ion. So from pH we can get the concentration of the hydroxide ion. II, explain how the student could use the measured value in part Fi to calculate the initial concentration of carbonate ion. Do not do any numerical calculations. The weak base equilibrium constant that we're given, Kb, equals the product of the concentrations of bicarbonate and hydroxide ions divided by the concentration of carbonate ion, and that is equal to 2.1 times 10 to the negative 4. And so there are two parts to this part II. So the first is to use the value from part I, and secondly, to calculate the initial concentration. So the value obtained from part I is pH, because we're taking the pH using a pH meter. So how can we use that value to calculate the initial concentration? Well, if we look back to part F, we see that it says the student decides first to determine the OH- concentration in the solution so that we can use that result to calculate the initial concentration of the carbonate ion. Then part I wants a method to determine OH minus concentration. And now in part II, it wants us to use the value from the previous part, which was pH. So let's use pH to calculate OH minus, because part F says that in order to calculate the initial concentration of carbonate ion, we first need to calculate the OH minus concentration. We know that pH plus pOH equals 14, so 14 minus pH equals pOH. And pOH really means the negative log base 10 of the concentration of OH minus. Negative pOH is equal to log of the concentration of hydroxide. Then we'll do 10 to the power of each side to get rid of the logarithm, and we are left with the concentration of hydroxide ion is equal to 10 to the negative pOH. And now we want to calculate the initial concentration of the carbonate ion. So let's write up a rice table to organize all our values. So the reaction is given above, so CO3 2 minus plus H2O liquid is in equilibrium with bicarbonate and hydroxide. Liquid water we will ignore. And so what do we know about the initial condition? Initially we have 0 bicarbonate and 0 hydroxide. And we have some concentration of carbonate. So we'll just call that C. It's an unknown. And then the change, we can look at the coefficients. Here the coefficients for everything are 1. So we subtract X from the reactant and add X for both the products. So at equilibrium, we go from initial minus X for carbonate, so that's C minus X. For bicarbonate, 0 plus X, and for hydroxide, 0 plus X. And now let's utilize the weak base equilibrium constant. So Kb is equal to the concentration of bicarbonate times the concentration of hydroxide over the concentration of carbonate. So concentration of bicarbonate is X, multiplied by the concentration of hydroxide, which is X, divided by the concentration of carbonate at equilibrium, so C minus X. All of these are the concentrations at equilibrium. And what the question asks for is the initial concentration of the carbonate ion, which is C. So we need to isolate C in this equation. So we'll do Kb times the denominator, C minus X, is equal to X squared. C minus X is equal to X squared over Kb. And finally, C is equal to X squared divided by Kb plus X. So a little algebra, and we can get an expression that represents the initial concentration of carbonate ion. And we're not doing any numerical calculations, we're just algebraically getting an expression that represents the initial concentration of carbonate. So use a rice table, organize your thoughts, and don't forget that it asks how the student could use the measured value in part I. So this portion is also important because you have to show that you're using the pH to calculate the OH concentration, which, if we were solving this numerically, we would have to use because the OH concentration is X. And even in our final expression down here, X appears twice, and we're given Kb, so it would be trivial to calculate C if we had a concentration of OH minus and we're given Kb, so it would be easy to do, but they don't want us to do any numerical calculations, so we will not. Okay, part G. Part G. In the original sodium carbonate solution at equilibrium, is the concentration of bicarb greater than, less than, or equal to the concentration of carbonate? To determine whether reactants or products are favored in an equilibrium, we can use the equilibrium constant. And as a general rule, if the equilibrium constant is large, then products are favored because the numerator in the equilibrium constant is large, and that represents the products. But if the equilibrium constant is small, then the reactants are favored at equilibrium because the denominator, which represents the concentration of reactants, is larger. Right, because KEQ is equal to products over reactants. So if the product concentration is very large, then KEQ should be very large, or at least greater than 1. And if the reactants concentration is very large, then KEQ will be small. And what we see here is that KB is very small. So that means that the reactants are favored. Reactants are favored. And that means that CO3 2- will be favored. So the concentration of bicarb will be less than that of CO3 2-. Part H, the student needs to make a carbonate-bicarbonate buffer. Is the sodium carbonate solution suitable for making a buffer with a pH of 6? Explain why or why not. So we're aiming to make a buffer with a pH of 6. What do we know about buffers? Buffers are effective at buffering pH when the acid that's being used has a pKa that is close to the desired pH. So if the pH we want for the buffer is 6, that means that we want the pKa to be also close to 6 for the acid that we're using in our buffer. And what's our acid? It's the HCO3-. So what is the pKa of HCO3-? We can calculate it. We know that the Kb is equal to 2.1 times 10 to the negative 4. Kw is equal to Ka times Kb. We get that straight from our equations page. We know that Kw is equal to 1 times 10 to the negative 14, and we have Kb, so we can solve for Ka by dividing Kw by Kb, and we find that Ka is equal to about 4.76 times 10 to the negative 11. We want pKa, which is the negative log base 10 of Ka. So if we take the negative log of 4.76 times 10 to the negative 11, we find that the pKa is equal to 10.32. Is 10.32 close to the desired pH of 6? No, it is not. So the sodium carbonate solution would not be suitable to prepare the desired buffer because the pKa of the weak acid that we would use for this buffer is not close to the pH of 6, that is the desired pH that we want to buffer. Since 10.32 is not close to the desired buffer pH of 6, the sodium carbonate solution would not be suitable to prepare the desired buffer.